Welcome to S Chemistry. I'm your instructor, Dr. Suhas Gaudi. I will be teaching BSc 5th semester Physical Chemistry course on nanomaterial. Here is the outline. In this lecture, I'm going to cover first, I will introduce about the nanomaterials, followed by methods of synthesis, in that high energy ball milling. Second, physical vapor deposition with consolidation. Third, chemical vapor deposition. Now, first we will see introduction. So, the word nano means 10 to the power minus 9. That is 1 billionth. 1 nanometer is 1 billionth of a meter. The nanometer is abbreviated as nm. That is nanometer. Now, the nanoscience and nanotechnology are the two of the latest field in today's scientific and commercial world. So these two fields are related to scientific and as well as commercial world. Nowadays, so many nanotechnology based uh, nanotechnology are coming. So this is the current topic which is in focus. So Richard Feynman is considered as a father of nano. Here you can see how where the nano word in terms of measurement it comes into the scale. So as you go down, so this is 10 to the power 1. So this is deca, 10 to the power minus 1. This is deci, it's a decimal. 10 to the power minus 2 means a centimeter, as we know 1 centimeter. So this is the unit of 1 centimeter. Now you can think about the nano. So that is the 10 to the power minus 9. So 10 to the power 3 minus 3 is milli, 10 to the power minus 6 is micro, that is denoted by mu. 10 to the power minus 9 denoted by n, that is nano. And 10 to the power minus 12 is denoted by pico, that is small p. If your length is in 10 to the power minus 15, we call it femto. And if your length is 10 to the power minus 18, we call atto. So this is the smallest of all unit in terms of any meter, second or anything. So as you go down means higher level on higher scale, so the symbol is respective and prefix are given below. So 10 to the power 1 is, we say, is deca, denoted by dA. If it's 10 to the power plus 2, then it's a hecto. If 10 to the power 3, we call it a kilo, denoted by k. If 10 to the power is plus 6, we call it mega, that is m, capital M. If it's 10 to the power plus 9, we call a giga, capital G. If it's 10 to the power plus 12, we call it tera, T. If it's 10 to the power minus plus 15, we call a penta, so P. If it's 10 to the power 18, we call exa, it's E. So like that. So now you can think about the plus and minus. So both we have seen. So this is the well-known centimeter, 1 centimeter, and pico nano is less than 1 centimeter. So you can think about how much small that unit is. So in that region we have to play the chemistry. So there are some terms involved in this chapter that I'm going to discuss now. First term is the nanomaterials. So the material, what is the definition of nanomaterial? So the matter which has dimension in between 1 nanometer to 1000 nanometer, we call it a nanomaterial. So your dimension of any material which is lie in 1 nanometer to 1000 nanometer, we call it nanomaterial. The second term is there, that is the nanoscience. This, what is meant by nanoscience? So it is a branch of chemistry for the study of a fundamental principle of a molecule and material with dimension between 1 nanometer to 100 nanometer. So is called the nanoscience. So if your dimension is between 1 nanometer to 100 nanometer, then if whatever the material is that, if you are studying that material and principle of the molecule, we call it a nanoscience. So this is the second term. What is the third term? That is the nanoscale. What is meant by nanoscale? The dimension which is expressed in nanometer or 10 to the power minus 9 meter is called the nanoscale. So it's just 1 nanometer, you can say in that way. If you can express in terms of nanometer, then we can call it it's a nanoscale. A third term is there, that is nanotechnology, a fourth term. So what is the fourth term? Nanotechnology. So it's a branch of engineering which based an application of nanomaterial into useful nanoscale devices is called a nanotechnology. So this is a branch of engineering which based an application of nanomaterial into useful nanoscale devices. So we call it nanotechnology. I hope these four concepts are clear. Now we will move to the next point, that is the method of synthesis. There are so many number of methods are there to synthesize the nanomaterial. First we will see what is meant by method of synthesis. So various techniques and methods of synthesis are available for different type of nanomaterials. Now we are going to see what are the methods. So broadly these methods are classified into four types, that is physical method, second is chemical method, third is biological method, and fourth is hybrid method. So any two can combine and form one method. So these four types of methods are there to synthesize any nanomaterials. So there are large number of techniques available to synthesize different types of nanomaterial in the form of colloids, cluster, powder, tubes, rods, wire, thin films, and etc. So these are the shapes of the nanomaterial. So your shape of the nanomaterial can be colloids, cluster, or in the powder form, or tubes, rod forms. So we can see now in the given figure. So this is also can classify in terms of dimensionality, 0 dimensional, 1 dimensional, 2 dimensional, and 3 dimensional. Some nanoparticles stays in 0 dimensional. That means these are the nanospheres or clusters, such as quantum dots, fullerene, or gold nanoparticle. So these are the 0 dimension because it comes less than 1 nanometer or 1 nanometer. So that's why we consider as a 0 dimensional. What is mean by 1 dimensional? So in 1 dimensional, there are examples are nanotubes, nanowires, and nanorods. So here, as you can see in this figure, so metal nanorods are in this kind of shape. So this can be any material, a metal or any ceramic crystal. So these are the nanorods or nanotubes. Uh, there are another example is carbon nanotube, which is made up of only carbon moiety, and it is in tube kind of shape. So that's why this is one dimensional nanomaterial. Other example is a nanowire. So that can be any length, and this length can be in terms of n number of flexible nodes will be there. So gold that can be gold nanowire. Examples are gold nanowire, polymeric nanofibers, or self-assembled structure. So these are the nanowires. So now 2D. Now we are going to see 2D, two-dimensional nanomaterials. So this is also one kind of classification in terms of dimensionality, but as given here the material types and form of the types. So here thin films comes in 2D. So you can coat it using as a spray technique like that carbon coated nanoparticles or graphene sheet, or can be layered nanomaterials. So these category comes in two-dimensional nanomaterials. What about three-dimensional? So in three-dimensional, generally bulk nanoparticle will come or polycrystalline. So these materials like liposomes comes under three-dimensional nanomaterials. So liposomes are present in our human cells and as well as animal cells. So another example is polycrystalline material, that is also three-dimensional nanomaterial, or and dendrimer. So this is a polymeric nanomaterial. This is recently synthesized. So these are the four types of classified in terms of dimensionality and in terms of shape. These are the shapes of the nanomaterials. Now we will move further. So now we are going to see methods to synthesize a nanomaterial. So this is the first method that we are going to see, that we are going to learn in this lecture, that is high energy ball milling. So what is high energy ball milling and how to synthesize? So it is one of the simplest way of making nanoparticle of some metals and alloys in the form of powder. So it is one of the simplest way of making nanoparticles of some metals and alloy. So in the form of powder. So this high energy, it's meant for only metals and alloy. So there are many types of mills such as planetary, vibratory, rod, a tumbler, etc. So these are the mills of the making balls, that is high energy ball millings. So planetary, vibratory, rod and tumbler. So these kind of rotational motions are there to synthesize nanomaterials. Usually one or more containers are used at a time to make large quantity of fine particles. So for to synthesize this nanomaterial, we have to use one or more number of containers. So that can be used multiple times for to make a large quantity of a fine particle. The size of the container of course depend upon the quantity of interest. So how much quantity you want to make, so that much we have to take the size of the container. So it depends on the how much quantity you want to make of the nanoparticle. Fifth point is the hardened steel or tungsten carbide balls are put in containers along with powder or flakes that can be less than 50 micrometer of a material of interest. So hardened steel or tungsten carbide, so these two types of material can be used to synthesize nanomaterials. So this is generally balls. So this is very highest tensile and this material can crush any kind of material and makes the powder in the powder form of or flakes form. So the size whatever you are putting into the that in ball milling, that size has to be less than 50 micrometer. So that is the one condition. The initial material can be of arbitrary size and shape. So that can be any shape like square, hexagonal, triangular, rectangular, cubes, a traploid, any kind of thing. And if you put that material shape of material if you put in the high energy ball milling, and you have to close the container with tight lids. Then you have to take 2:1 mass ratio of ball to material is advisable. So your ball suppose is 10 kg and your metal should be like 5 kg. So like that ratio you have to take to obtain a good quality of nanomaterial, a fine quality of nanomaterial. If the container is more than half filled, the efficiency of milling is reduced. So if you filled more than half, your efficiency of the milling will be reduced. Heavy milling balls increase the impact energy on collision, and a larger ball used for milling produce a smaller grain. If you use larger ball, you will get the smaller grains size, but the larger defect in the particles. So this you have to take in proportion only. You cannot take more which is having higher radius of the ball and the smallest grain. If it form also, you will get more defect in the particle. So your particle size will not be uniform. So that is the drawback of the system. So such particle would prefer to acquire a stable lower surface energy state. The container are rotated at high speed, a few hundred of RPM around their own axis. So additionally, they rotate around some central axis and therefore we call it a planetary ball mill. So now you will see the figure of the ball milling, then you can understand better. So this is the schematic diagram of and this is cross sectional of a ball milling vessels. So you will be having a container. So this is half filled, and the you cannot rotate this container with high RPM. So you have to keep it in few hundred RPM around their own axis. So therefore, additionally, they rotate around the some central axis, and therefore call it a planetary ball mill. So that's why we call it a planetary ball mill. So that's why the name is planetary, because it rotates in that way, in planetary way. So by controlling the speed of rotation of the central axis and the container as well as duration of the milling, so it is possible to ground the material to fine powder. So that's how we have to find the material. So you have to control the speed of rotation. So your speed of rotation can be, if you keep how much speed, that type of you will get the nanomaterial size. If you keep higher speed, you will get very fine nanoparticle, and if you keep for longer time also, you will get very fine particle. So that fine powder you will get in terms of few nanometers to few ten, tens of nanometer, so whose size can be quite uniform. So some of the material like cobalt, chromium, tungsten, nickel, tin, aluminum, iron alloy, and gold iron alloy are made nanocrystalline using ball mill. So these are the materials which can be using high energy ball milling. You can make the nanomaterials like cobalt, chromium, tungsten, nickel, tin, like that. So these are the metals. Our procedures are well known to synthesize nanoparticle of these metal atoms. So this is the application of high energy ball milling. Now we are moving to the second point, that is physical vapor deposition with consolidation. So we will see second method to synthesize nanomaterial. So as the word suggests, physical vapor means your whatever the material that is coming into the vapor form, that's getting deposited with consolidation. Now we will see the how the technique works. So this technique basically involves a use of material of interest as source of evaporation. So for evaporation, we have to use as inert gas or reactive gases for collision with a material vapor. So that is the condition. So you have to use inert gas or reactive gas. You can use. If you are taking a reactive gas, it will form with your nanoparticles. That is the side product will form or main product will form after reaction. So generally, the reactive gas is nothing but your oxygen. So in terms of if you have to make the some particle oxidize, element oxidize, then you can use the reactive gas. Otherwise, you can use the inert gas for evaporation. So there will be the cold finger on which cluster or nanoparticle can condense. So after evaporation, you will be having one cold finger, so on which your cluster or nanoparticle can condense. So whatever the nanoparticle that he has to form or synthesize, it will go to on cold finger. So you will get nanoparticle there. As a scraper or to scrape the nanoparticle and piston wheel and wheel, an arrangement in which nanoparticle powder can be compacted. So usually metals or high vapor pressure metal oxide are evaporated. Generally there are some metal oxides that is used to get evaporated. High vapor pressure with high vapor pressure. Or you can directly sublimate from filaments or boot of refractory metals like tungsten or thallium and molybdenum. So these three types of metals are there where they use as a refractory metal. So in which material to be evaporated are held. So these are the like material of the container, tungsten, thallium or molybdenum. So these three types of materials are generally used to synthesize the nanoparticle or to make the high vapor pressure metal oxide to get evaporated. Next point is the density of the evaporated material close to the source is quite high and particle size is small, that is less than 5 nanometer. So whatever you are making evaporation, that density should be evaporated material close to your the source and it is quite high. So therefore your particle size will be less than 5 nanometer. It will form. Now we will see what is the point we have to take in account to synthesize a uniform nanomaterial. So in general, the rate of evaporation and the pressure of the gas inside the chamber that determine the particle size and their distribution. So distance of the source from the cold finger is also important. So how can you control the nanoparticle size? So using rate of evaporation, that is the first your parameter. Second parameter is the pressure of the gases inside the chamber. So this is the second parameter. And third parameter is the distance between source and the cold finger. So how much distance is there depending on that how much thin layer you want to synthesize. So based on these three parameters we have to decide. So what is the advantage of this technique? The particle size can be controlled by adjusting the pressure of the inert gas or the rate of evaporation and the distance between the source of the evaporation and the central cold rod. So on these 4 points, so these are the variables where particle size is dependent. Second point is amorphous or crystalline nanoparticle. So these both type of nanoparticle can be synthesized by the controlling gas pressure in deposition chamber. So if you control the gas pressure, uh, if it's high, you will get the crystalline. If it's high, you will get amorphous. If it's slow, you will get the crystalline material nanoparticle. So you have to just control the gas pressure inside the deposition chamber. So this is the general schematic diagram of synthesis of nanoparticles by physical vapor deposition. So as you can see, this is your chamber. So this is your, you have to attach this chamber with vacuum pump just to remove whatever the inside reactive gases is there, and then after this complete applying vacuum we have to put the some gas. That is, for that we have to have this gas inlet. So using this inlet you can purge your gas inside the chamber. So this is the piston and wheel. So for this, the use of this is just to adjust the distance between your funnel and the cold finger. So this distance you can control using this piston. So this is the funnel where your material will get evaporated or get heated up. So based on this temperature you can decide your rate of evaporation. So side there will be crucible. So crucible has the work just to crush the material or just to evaporate the nanomaterial in uniform form. So this is the cold finger, where inside cold finger you will be having liquid nitrogen. So this is the central rod, and this is very important in terms of to get your condensation at particular time or fixed temperature. So based on this temperature your nanoparticle size will be dependent. And this is the scraper. So in this scraper, this is important just to adjust the height of the cold finger. So these are the parameters and component of the physical vapor deposition chamber. Now we will see the third method of synthesis of nanomaterial, that is chemical vapor deposition. We also call it CVD. So in this method, what is this method? So this method is about a chemical which get react in vapor form. So deposition take place in vapor form. So the definition is given here. A hybrid method using chemical in vapor phase is conventionally used to obtain coating of variety of inorganic or organic materials. So this method is hybrid. So it's both physical and chemical. So both methods are mixed. So here your chemical first get in vapor phase, and this is conventionally used to obtain the coating of a variety of inorganic and organic materials. So now we will see what are the basic chemical vapor deposition processes. So as you can see in figure 5.3, it's given here. So this solid dots represents the gaseous reactant, cross dots represent the intermediate product, and blind dot represent the solid product, and square symbol represent the gaseous product after reaction. So now we will see the method with step by step how it's are going to fall on this substrate. So this is the first point. First, your transport of reactant vapor towards the substrate will come. So these are the solid dots. These comes to the towards the substrate. So this is the first process. Then this reactant get cracks into different product on this high temperature surface. So this substrate surface is having very high temperature. It get cracks on this surface, and after getting cracks you will be having multiple products. These products get diffused on the surface and undergo some chemical reaction with other. So after reaction, chemical reaction, it start getting nucleate, and nucleation will take place and it will grow. to form the desired material films. So as you can see, this solid products formed, and it is forming a particular desired film. So this is because of nucleation, and further, if you this process continues for a long time, this will grow and form the thin film. So this is the gas inlet. So with this reactant, you are coming with a gas, inert gases, and here it get reacted and form the films. So after forming film, you will be having some byproducts created on the substrate that has to have to transport back to the gaseous phase. So this square is your byproduct. So these byproduct are going outside the sample, outside the substrate. So it will go in the vapor phase, and that's or gaseous phase, and that's how your CVD process is going on. Now we will see there are two types of processes are there. So one is hot wall chemical vapor deposition, and second type is the cold wall chemical vapor deposition. So this is the schematic representation of hot wall chemical vapor deposition, and this is the schematic diagram for the cold wall chemical vapor deposition chamber. So in both cases, you will be having vapor inlet and exhaust, it is outlet. So the only difference is your outside the wall will be having some heater, and in cold wall you will not be having this kind of heater. Now we are going to see what exactly happens during the process. So as you can see in this figure, the vapor of a desired material may be often pumped into reaction chamber using some carrier gas. In some cases, reaction may occur through aerosol formation in gas phase. There are various processes such as reduction of gas, chemical reaction between different source gases, or oxidation, or some disproportionate reaction by which chemical vapor deposition can proceed. So these are the four types of reaction can happen in the this hot wall chamber. So however, it is preferably that reaction occur at the substrate rather than in the gas phase. So usually 300 to 1200 degrees Celsius temperature is used at the substrate. So I am talking about this substrate temperature that can be go 300 to the range of the substrate temperature is the 300 to 1200 degrees Celsius. So there are two ways is there. So one is using heater, another is using a filament. So in hot wall setup, the deposition can take place even on a reactor wall. So your deposition can take place on reactor wall also. So this is avoided in cold wall design. So here your substrate will not get your reactant will not get deposited on cold wall. So this is the plus point for the cold wall diagram. So besides this, the reaction can take place in a gas phase with hot wall design, which is suppressed in cold wall setup. Further, coupling of plasma with chemical reaction in cold wall setup is feasible. So coupling of plasma in this here, it is possible in cold wall setup. So usually gas pressure in the so inside some particular gas pressure will be there, so that that is the range is from 100 to 110 to the power 5 pascal are used. So growth rate and film quality depends upon the gas pressure and the substrate temperature. At intermediate temperature, it is limited by mass transport, that is, supply of reacting gases to the substrate. Here, the reaction is faster and supply of reactant is slower. So, growth rate produce at high temperature, growth rate reduces due to desorption of precursor from the substrate. So these are the two differences are there for hot walled chemical vapor deposition and cold walled chemical vapor deposition. Now we will see advantages of chemical vapor deposition. So this technique is widely used in industry because of the following reasons. So first reason is it is a relatively simple instrumentation. Second is the ease of processing. So the process is very easy. Third point is possibility of depositing different type of material. So here various type of possibilities are there to for the deposition of material. Fourth point is it is economically viability is there. So that's why this is widely used in industry. So for example, if you want to make nanocrystalline films or single crystalline films, you can use this kind of method. So that is the chemical vapor deposition. Now we will see what are the variants of chemical vapor depositions are well known in the literature. So first variant is the metallo-organic chemical vapor deposition, that is MOCVD. The second variant is their atomic layer epitaxy, that we also say that ALE. Third point is vapor phase epitaxy, that is denoted by VPE. The fourth variant of chemical vapor deposition is plasma enhanced CVD, or in other word PECVD. So they differ in, so these are the four type of models are there or variants are there, where you can either change the source of the gas pressure or the geometrical layout and the temperature, what are the temperature we are using for that. So these are the three different parameters are there. So with these three parameter, these four variants are uh, can be changed, and relatively you can get the your nanocrystalline material or films. So these are the references for this lecture. For images and for the content, these two books student can refer. So here we came to end of this lecture. Thank you for your kind attention and see you in next lecture. Till then, happy learning.